Hello YouTube, my name is Ali and welcome back to another video. Today we're going to be starting some binary exploitation for beginners. This video may get a bit lengthy, but please do stick around. This is the first video in a series I plan to do on binary exploitation for beginners, and today we will be covering the C language and how it is often susceptible to a buffer overflow. This is because C is such a low-level language that it will do exactly what you tell it to do, even if that's not exactly what you want it to do. So you should always know exactly what your program will do. Binary exploitation is more often than not a matter of intuition. If I can cause a program to crash in a certain way or cause some weird behaviors, then my intuition would tell me that I might be able to exploit it via one method or another. Now, before we start, I will say that I'm not an expert, so there may be some mistakes. If this is the case, feel free to correct me in the comments, and I will do my best to correct the video. Quick notice, this is my first scripted video, so I may get lost for a few seconds at a time. Let's dive right in. I've already prepared a small program that I know is exploitable, and that's what we will be using in this video. All of the source code will be made available through a link in the description, so feel free to follow along at home. Yes, I know it's like 20 lines, but still. Let's take a look at this small program. If we go down to line 16, we can see int main. In C, this function is recognized by the compiler as the main function for the program, or the entry point. This is always where code will start execution. On line 17, we can see a call to printf. If you're a complete newbie to C, you might be thinking, hang on, shouldn't this be print? In many other high-level languages, such as Python, you would call print to output something to terminal, but with C, there is no print function. Printf just means print formatted. It is a special function that takes a special format string and as many parameters at once. And prints the string formatted with the parameters as specified by the format string. Fortunately, we don't need to know that in this case, but generally printf is used to print a string to the terminal. Moving on to line 18, we can see a call to our function vuln. If we go to line 8, we can find our function vuln. Another thing to note is that in C we program from the bottom up. So you can't generally call a function that is defined below you. For example, with this code, we would not be able to call vuln from within win. Anyways, vuln declares a local variable buffer, which is an array of characters that is 32 long. This is one way to define a string in C. Next, the function gets is called with buffer as a parameter. Since buffer is an array, it actually points to the first element in memory, so gets knows where to find that and can write to it. However, gets is a very dangerous function. If we take a quick look at the man pages for gets, the first thing in the description is never use this function. This is because gets reads a line from standard in into the buffer pointed to by s, until either a terminating new line or an end of file, which it replaces with a null byte or string terminator, and no check for buffer overrun is performed. This can cause it to overrun into memory that is not a part of the buffer. Often this will cause a program to crash, but if done carefully, the program can be exploited and the return address of a function can be overwritten. Once the buffer has been read, puts is then used to print the buffer to the terminal. Vuln then returns into main, which returns and exits the program. So our program has finished executing, but we haven't called the win function. How do we do that, you might be asking? Well, that's what binary exploitation is about. Redirecting code to make a program do what we want. So let's compile our vulnerable program using GCC and see what happens. We can use gcc vuln.c -o vuln. As you can see from the compiler output, there is a warning that gets is a dangerous function and should not be used, but we are going to ignore that for demonstration purposes. Now, if we run vuln with /vuln, we can see the prompt, please put your input below. If we just put some random input, we can see that it just gets printed out again. But if we make that input longer, we get a message stack smashing detected. This is because modern compilers include a stack cookie before the return address. Every time a function returns, a system call is made to ensure that the stack cookie has not been modified. If a buffer overrun occurs and the return address is overwritten, the stack cookie must also have been overwritten or been modified. If it has, the kernel realizes that the program has had the stack overwritten and terminates the program immediately to prevent code redirection, or in some cases, arbitrary code execution. Since many programs are compiled without this security measure, we are going to disable it in GCC, again for demonstration purposes, by using the argument -f_no stack protector. I strongly recommend that you do use this feature with your code. This just disables stack protection for this compilation, allowing us to continue with the demonstration. Now that we have recompiled our program without stack protection, we can run it again with the same input. Well, this time we get a segmentation fault. This is where you should start to gain an intuition for binary exploitation. Whenever you see a segmentation fault that is caused by user input, that generally means that the program has a high potential to be exploited. This is because a segmentation fault is caused when the program tries to read or write to unmapped memory regions. Most commonly, this is caused by the instruction pointer being overwritten. If we can control the instruction pointer, we can control where the program executes, and we gain code redirection. Let's run our program with GDB, the GNU debugger, and see what happened. See exactly what caused the crash. I have a plugin for GDB called Payda, which has a few useful tools linked below on how to install Payda. We can use the command run to run our program, and then we input our data. As we can see, the program stopped in vuln due to a sigsegv, or segmentation fault. If we use the command backtrace, we can see that the function that called vuln is at the address 414.141.41 or AAAA. Of course, this is not correct, but it means that our return address has been overwritten. This is very dangerous, because by changing the input string, we can precisely control where the instruction pointer goes to. To control our instruction pointer, we need to put the hexadecimal values into our string. Unfortunately, we can't just type them, because not all of the values are printable ASCII characters. So instead, we are going to write them to a file. If we use a command called echo, we are going to echo our string, which is and use escaped characters to print our hexadecimal file. So echo -e and paste in our string. We are now going to include our address. If we go back to VS Code, we can... but there are a few things we need to know. Firstly is that modern processors use what is called little endian. This is where each byte is stored most significant bit first, but groups of bytes are stored least significant byte first. So we need to know what the hexadecimal that we are going to use is. To find this, we go back to GDB and use the command x examine to examine the function win. This gives us the address of hexadecimal 555555555155. We can now take this and use it in our file. So now that we have our file in.txt, which has 32 plus 8 bytes of padding and the 6-byte address of win, we can run our program with in.txt as the input. We're going to take this over to GDB and do that by using run with in.txt. I've already set a breakpoint at the return from vuln, so upon running this we can see we're in vuln, and if we do the command backtrace we can see we are in frame dummy. But if we have a look at win, we can see that this is exactly the same address, and by continuing we can see that we are now in the win function and we have successfully gained code redirection. I hope you enjoyed this video. If you did, please leave a like, share the video with some friends, subscribe, and leave any feedback in the comments below. I will do my best to respond to all feedback. I hope you enjoyed, and I will see you next time. Goodbye.